NENOMATICA, where mathematics meets YouTube excellence. Welcome to this mathematics video, where we'll prove an inequality step by step. Let's take a look at the inequality we need to prove. Here's our example. We need to prove that the square root of the quantity a plus c multiplied by b plus d is greater than or equal to the square root of ab plus the square root of cd. Now let's solve this step by step. For our first step, we'll apply the rule that if both sides of an inequality are non-negative, we can square both sides without changing the direction of the inequality. So we square both sides of our original inequality. On the left, we get the square root of the quantity a plus c multiplied by b plus d squared. On the right, we get the square root of ab plus the square root of cd squared. For our second step, we'll simplify the left side and expand the right side using the binomial square formula. The square of the left side simply becomes a plus c times b plus d. For the right side, we use the formula for the square of a sum. The square of a sum equals the sum of squares plus twice the product. So, the square of the square root of ab plus the square root of cd equals ab plus cd plus 2 times the square root of ab times cd. For our third step, we'll expand the left side using the distributive property. When we expand a plus c times b plus d, we get ab plus ad plus c b plus cd. Now, notice that ab and cd appear on both sides of the inequality, so we can subtract them from both sides. For our fourth step, we'll simplify the left side by canceling out common terms. After canceling ab and cd from both sides, we're left with ad plus cb is greater than or equal to 2 times the square root of abcd. For our fifth step, we'll rearrange the inequality to set up for our final comparison. We subtract 2 times the square root of abcd from both sides to get bc minus 2 times the square root of abcd plus ad is greater than or equal to 0. For our sixth and final step, we'll recognize that our expression is actually a perfect square. The expression bc minus 2 times the square root of abcd plus ad can be rewritten as the square of the square root of bc minus the square root of ad. Since a square is always greater than or equal to 0, our inequality is proved. Since the square of any real number is always non-negative, the inequality is proved. This means our original inequality is always true for any non-negative values of a, b, c, and d. Welcome to this mathematics video. Today we're going to prove the following inequality. The square of the sum of a, b, c, and d is greater than 8 times the product of a d plus bc, given that b is greater than d and is greater than c. Let's approach this problem step by step. We'll consider a quadratic function in terms of x and analyze its properties to prove our inequality. We define the function f of x equals 2x squared minus the sum of plus b plus c plus d times x plus the sum of the products a d plus bc. For this quadratic function, let's compute the discriminant. The discriminant delta equals the square of the coefficient of x minus 4 times the product of the coefficients of x squared and the constant term. So delta equals the square of a plus b plus c plus d minus 8 times the product of a d plus bc. Now, we observe that if the discriminant is positive, then the quadratic equation has real roots. So our goal is to prove that if b is greater than d and o is greater than c, then the discriminant is positive, which will prove our inequality. Let's evaluate this function at x equals a. F of it equals 2 times a squared minus the sum of plus b plus c plus d times a plus the product a d plus bc. Simplifying further, we get f of it equals 2 a squared minus ab minus ac minus ad plus bc, which simplifies to f of it equals a squared minus ab minus ac plus bc. We can factor this as f of it equals a squared minus ab minus ac plus bc, which can be regrouped as a squared minus ab minus ac minus bc. This further simplifies to a squared minus ab minus c times a minus b. And finally, we get f of it equals a minus b times a minus c. Similarly, let's evaluate the function at x equals b. Working through the same process of simplification and factorization, we find that f of b equals b squared minus a b minus bd plus ad. This can be rearranged as b squared minus ab plus ad minus bd. Factoring further, we get f of b equals b minus a times b minus d. Continuing in the same manner, let's evaluate the function at x equals c. After simplification, we find that f of c equals c squared minus cd minus ac plus ad. This simplifies to f of c equals c minus d times c minus a. Finally, let's evaluate the function at x equals d. After simplification and factorization, we find that f of d equals d minus b times d minus c. Now, let's analyze the signs of these function values. We're given that b is greater than d and a is greater than c. Let's consider the value of f at point A. We have f of a equals a minus b times a minus c. Since a is greater than c, the term a minus c is positive. However, we don't know the sign of a minus b, so we can't immediately determine the sign of f of a. Similarly for f of b, which equals b minus a times b minus d. Since b is greater than d, the term b minus d is positive. But we don't know the relation between b and a, so we can't determine the sign of f of b either. Let's continue our analysis. For f of c, which equals c minus d times c minus a, we know that c is less than a, so the term c minus a is negative. But we don't know the relation between c and d. For f of d, which equals d minus b times d minus c, we know that d is less than b, so the term d minus b is negative. But again, we don't know the relation between d and c. But what we do know is that our original quadratic equation will have real roots if the discriminant is positive. This means that if any two values a, b, c, or d satisfy a equals b or c equals d, then the discriminant becomes 0. In the general case where b is greater than d and is greater than c, and assuming a, b, c, and d are all distinct, our function will have two distinct real roots. This means the discriminant must be positive. Therefore, we have proved that the square of the sum of a, b, c, and d is greater than 8 times the product of a d plus bc. In other words, open parenthesis, a plus b plus c plus d close parenthesis squared 8 add plus bc when b greater than d and a greater than c. Welcome to our video on proving mathematical inequalities. Today, we'll be solving a challenging inequality step by step using algebraic techniques. Let's examine our problem. We need to prove the following inequality. 1/8 times the quantity a minus b squared divided by a is less than or equal to a plus b divided by 2 minus square root of a times b, which is less than or equal to 1/8 times the quantity a minus b squared divided by b. And we're given the constraint that it is greater than or equal to b. Let's start by focusing on the right-hand side of the inequality. We want to prove that a plus b divided by 2 minus square root of a times b is less than or equal to 1/8 times the quantity a minus b squared divided by b. Let's follow the solution approach shown in the algorithm. Our first step is to rearrange the terms to get the expression a plus b divided by 2 minus square root of a times b on the left-hand side. Now, we'll subtract square root of a times b from both sides. This gives us a plus b minus 2 times square root of a times b over 2 is less than or equal to 1/8 times the quantity a minus b squared over b. Let's observe that the numerator on the left side can be rewritten as the square of the difference of square roots. This gives us the square of square root of a minus square root of b, all divided by 2, is less than or equal to 1/8 times the quantity a minus b squared over b. Now, let's rearrange this inequality to compare the ratios of the expressions. We get the quantity a minus b squared divided by 8b times the quantity square root of a minus square root of b squared is greater than or equal to 1/2. Let's continue with our algebraic manipulation. We can rewrite this as the square of the quantity square root of a minus square root of b times the quantity square root of a plus square root of b divided by 8b times the quantity square root of a minus square root of b squared is greater than or equal to 1/2. Simplifying the expression, we know that the product of the sum and difference of square roots equals the difference of the original terms. So, square root of a minus square root of b times square root of a plus square root of b equals a minus b. This gives us the square of square root of a plus square root of b divided by 8b is greater than or equal to 1/2. Continuing our algebraic manipulations, we can equate this to the square of square root of a plus square root of b divided by 8b equals 1/8 times the quantity 1 over square root of b times the quantity square root of a plus square root of b squared. Simplifying further, we get the square of square root of a plus square root of b divided by 8b equals 1/8 times the square of the quantity square root of a plus square root of b divided by square root of b. Finally, we can write this as the square of square root of a plus square root of b divided by 8b equals 1/8 times the square of the quantity square root of a divided by square root of b plus 1. Now, given our constraint that it is greater than or equal to b, we know that square root of a divided by square root of b is greater than or equal to 1. So, square root of a divided by square root of b plus 1 is greater than or equal to 2, and the square of this quantity is greater than or equal to 4. Therefore, 1/8 times this quantity is greater than or equal to 1/2. So, we have proven that the square of square root of a plus square root of b divided by 8b is greater than or equal to 1/2. This confirms the right-hand side of our original inequality. The proof for the left-hand side of the inequality follows a similar approach. As the solution structure in the image indicates, the left-hand side inequality can be proven using the same techniques we just used. Both sides of the inequality are proven, confirming the full inequality. 1/8 times the quantity a minus b squared divided by a is less than or equal to a plus b divided by 2 minus square root of a times b, which is less than or equal to 1/8 times the quantity a minus b squared divided by b. Welcome to this mathematical proof video, where we'll show an interesting inequality involving nth roots. Specifically, we'll prove that for every integer n greater than or equal to 2, the following inequality holds. Let's begin by establishing our approach to prove this inequality. Instead of proving the entire chain at once, we'll focus on the general case. We'll show that for any n greater than or equal to 2, the inequality shown here holds true. Our proof strategy will be to show that the ratio of these terms is less than 1, which would confirm that the left term is indeed greater than the right term. Let's start our proof. Step 1. We'll rewrite the ratio of the nth roots in a more convenient form. We'll express both terms under a common root. First, we rewrite the ratio as the nth root of n plus 1 divided by the n minus 1th root of n. To convert this into a single root, we need to use the property of roots that says the ath root of x raised to the b power equals the a times bth root of x raised to the b power. After we simplify, we get this expression shown here. Step 2, let's continue simplifying our expression. We'll rewrite the numerator and denominator to highlight a term involving 1 plus 1 over n. First, we'll rewrite n plus 1 over n as 1 plus 1 over n. After simplifying the fraction inside the root, we get this expression. Step 3. Now, we'll use the binomial expansion to estimate an upper bound. The binomial expansion allows us to expand expressions of the form 1 plus x raised to the power n. We'll actually look at 1 plus 1 over n raised to the power n, which is slightly different from what's in our expression, but we'll make use of it. When we expand this using the binomial theorem, we get a series of terms. We can estimate this sum to be less than 3 for all values of n greater than or equal to 2. Step 4. Let's use our bound to complete the proof of the general term. From our previous step, we established that 1 plus 1 over n raised to the power n is less than 3 for all n greater than or equal to 2. From this, we can derive the following inequality. We multiply both sides by 1 over n plus 1. Since n is at least 2, the right side is less than 1. Taking the positive n times n minus 1th root preserves the strict inequality, giving us our desired result. Step 5. Now, we need to show that the expression we've been working with is actually equal to the ratio we started with. Through algebraic manipulation, we can verify that the n times n minus 1th root of 1 plus 1 over n raised to the power n times 1 over n plus 1 is equal to our original ratio. This confirms that the ratio is less than 1. Therefore, we've proven that the n minus 1th root of n is greater than the nth root of n plus 1 for all n greater than or equal to 2. Step 6. Finally, we need to show that the entire inequality chain holds. We've established that for any n greater than or equal to 2, the n minus 1th root of n is greater than the nth root of n plus 1. By applying this result repeatedly starting from n equals 2, we can see that the square root of 3 is greater than the cube root of 4, which is greater than the fourth root of 5, and so on. Since we also know that 2 is greater than the square root of 3, we've proven that the entire inequality chain is strictly decreasing. In today's video, we'll prove a challenging inequality involving reciprocals. Let's take a look at our problem. Let's start by simplifying each term in the inequality. We'll use a well-known formula for the sum of reciprocals. The left side of our inequality has two terms. The first term, 1 divided by the sum of 1 over a plus 1 over b, can be rewritten as ab divided by a plus b using our formula. Similarly, the second term becomes cd divided by c plus d. For the right side, we get the expression a plus c times b plus d, all divided by a plus b plus c plus d. So our inequality now looks like this. Now, let's eliminate the denominators to make our inequality easier to work with. We'll multiply both sides by the product of all three denominators. Since a, b, c, and d are all positive, the denominators are also positive, so multiplying won't change the direction of the inequality. Let's denote the sum of plus b plus c plus d as capital S to simplify our notation. After multiplying both sides by a plus b times c plus d times s, we get this expression. Now comes the challenging part. We need to expand all the products and collect like terms. This will involve multiplying out several expressions, which leads to many terms. Thinking face, think for a moment. Can you predict what our final result might look like? After careful expansion and cancellation of identical terms on both sides, we can reduce the inequality to a much simpler form. The difference between the right side and the left side equals a d minus bc quantity squared. Now, we've reached the final step. We know that any real number squared is always non-negative. Since a d minus bc quantity squared is always greater than or equal to 0, our inequality must be true. Therefore, we have proven that for any positive values of a, b, c, and d, the inequality 1 over the sum of 1 over a plus 1 over b plus 1 over the sum of 1 over c plus 1 over d is less than or equal to 1 over the sum of 1 over a plus c plus 1 over b plus d. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.